So welcome everyone to the Cognitive Computational and Systems Neuroscience Methodology Workshop. The theme of this workshop is open science. So this is the newest element of the CCSN graduate pathway. The idea is to focus on how to conduct high quality research in topical material that actually bridges the three constituent graduate programs, and that includes psychological and brain sciences, biomedical engineering, and systems neuroscience. So the content, the methodological content that we plan to cover in these workshops is intended to be general for these three programs and also general throughout research activities. So the format of this kind of workshop is intended to be accommodating to a wide variety of disciplines, and I'll get to that shortly. So I want to begin by introducing our guest speaker today, Dr. Julia Strand. So she took a PhD in psychology from Washington University with an advisor. Her advisor was Mitch Summers. She then pursued a postdoc in biomedical engineering in my lab, all the while working on speech perception, audiovisual integration, and she has now gone to set up her own lab at Carleton College on focusing on some of the same kinds of research directions and expanding to include issues of cognitive effort and a wider variety of variables that might influence these complex perception tasks. And also, what brings her to this workshop today is her work on more meta-scientific questions of open science, of construct validity, and measurement and error correction, which you'll hear about today. So the last point that I'll make is logistics for this particular workshop series. So the way that we're structuring this is in two parts. Today is part one. Part one is open to the wider CCSN community, and depending on how everything goes, we might consider opening up further. We want to prioritize the CCSN community, and especially the CCSN students. So I don't want this workshop to grow to an unwieldy size, for example. But we are piloting it with this particular format. And the format today is up to an hour that we will provide Dr. Strand to present the material that she has prepared related to her work on open science. Then we are reserving another entire hour for dialogue. So the students in the ACCSN class will be present for this extended period. But by dividing it up in this way, we acknowledge that different members of the community might be more interested or available for particular aspects of it in this form. So given that we want to focus on the dialogue in the second half, what I would ask anyone who has questions when they emerge to compile them or to type them, compose them into chat, and then Shelley Cooper, the other instructor for ACCSN this semester, or I will moderate them, probably by compiling them in preparation for the discussion section. And then part two, if Dr. Strand has an element within her presentation that is open for discussion, she will invite discussion at that point. But otherwise, I'll just ask you to hold your questions until the end. Part two is dedicated to the CCSN students. But if you're interested, if you find this material compelling, please contact me. I'd be willing to open up the Wednesday session for others as well, but there's homework involved. And so you'd need to be prepared for that. That's my introduction. And with that, I will turn the floor over to Dr. Strand.
Thank you so much. Thank you, Dennis, for that introduction and for the invitation to be here. I'm really excited to be back at WashU and have the opportunity to share some of my recent meta-science work and perspectives on open science. It's also very nice to see some familiar names and former professors in the audience. So Dennis and Shelley asked me to give a general overview into some issues related to transparency and replicability, and also share some reflections about my own personal journey and the process of navigating these issues. So I'm going to do both of those things today and in that order. So one of the cornerstones of the scientific process, as I'm sure all of you know, is that work can be independently replicated. So if I do a study in my lab and report some particular finding, another lab should be able to independently replicate that effect. If studies don't replicate, if there is inconsistency in the results, that can be cause for some concern. So perhaps the original finding was a false positive, that is a finding that was identified when it was not in fact true. It's also possible that the replication attempt was a miss or a false negative. Or perhaps there was some unintended difference between the two experiments that accounts for the deviations. So maybe the experiments were conducted in slightly different ways, intentionally or unintentionally, and the changes between the experiments substantially affected the outcome of the study. It's really important to note that a failure to replicate does not necessarily mean that the original study was wrong and the new study is right. There's kind of often a sense of this when you hear people talk about studies failing to replicate. And I think it's really important to emphasize that a different finding in a newer study than an older study needs to be taken in context, because there are lots of ways that you can mess up a replication attempt that lead to very different results from the original. So a failed replication can mean many different things, and it requires careful scrutiny to figure out whether a new attempt that found something different than the original actually threatens that original finding. All right, so there have been murmurings of concern in the science that research may not be as replicable as is generally assumed or as we would like. So in 2016, there was a survey reported in Nature that revealed that 70% of scientists who responded have tried and failed to reproduce someone else's experiments, and more than half have failed to replicate even their own experiments. Then in 2015, the Reproducibility Project set out to replicate 100 recently published studies and found that the replication attempts were far less likely than the original studies to render statistically significant results. So the panel you see now is showing the p-values for the original studies, which were generally very small, and the replication attempts, which tended to be larger, that is less likely to be statistically significant. And the project also showed smaller effect sizes in the replication attempts than in the original studies. So these low rates of replication have replicated in other kinds of comparable projects. And this really became a turning point. This study, although it wasn't the only turning point, was an important turning point in what is now being referred to as the replication crisis. Cue minor chords. So many people in the field have become really concerned, right? Lots of studies have failed to replicate. Which are next? What can we trust? Will one of my studies be selected next and fail to replicate? How much policy is based on these studies that may in fact not be true? And as the crisis has played out, it's become clear that this is not psychology's problem. We might be a particularly egregious offender for reasons I'd be happy to talk about later, but this is science's problem. And the factors that led to the replication crisis in psychology are present in lots of disciplines. My favorite doom and gloom headline of about this time is "Everything is crumbling." So it appears that science is broken, we can trust nothing. Thank you for coming to my talk. That is all. No. Okay. So these results clearly indicate that something about how we are doing science may be amiss. The concern is that the scientific record, the collection of facts that we have collectively spent our careers assembling, may have errors in it, right? There are findings that don't hold up. But there are places that we have collectively been wrong. But on some level, we all know this, right? Some things in the literature aren't true. Everyone understands that. If it is 1%, if it's 5%, we might say that's just part of doing science. by chance you would have that many false positives in the literature. We can't avoid that. And if we set up a system to ensure that there were 0 false positives that ever made it to the literature, that would have much worse repercussions. So some amount of things being false positives in the literature is inevitable. But what if rather than 1% or 5%, it's 20%, or it's 40%, or it's 60%, right? At some point, we have to say, this is a problem that needs to be addressed. So the concern that I'm going to be focusing on today is about the factors that lead to false positives in the literature. So reported findings that don't actually reflect the true state of the world. As just a brief caveat, though, we have to ask, why don't we worry as much about the consequences of false negatives in the literature as we do about false positives? Well, one reason is publication bias. The fact that journals are far more likely to publish studies that have statistically significant results than those that do not. So this leads to what's referred to as the file drawer problem. Statistically significant results go in journals and non-significant ones go in file drawers. We don't speak of them ever again, so nobody knows about them. And that leads to a very skewed perception, a very skewed representation of what's actually in the literature. And indeed, there are not many null results in the published literature. A review of rates of positivity, that is the proportion of findings that show statistically significant support for the hypotheses, revealed that the vast majority of published studies found support for the hypotheses presented. Psychology, down at the bottom there, is over 90%. So over 90% of published studies were reporting statistically significant support for the hypotheses. So if we look at all of the studies in the published literature, and we note that the vast majority of them have statistically significant effects, there are a few different reasons that might be the case. So first, maybe the literature is full of statistically significant findings because scientists are very smart and we only ever hypothesize things that end up being correct. So maybe we are all just really good guessers. It may also mean that there are other studies that are out there that have been conducted that don't get published. So this is in line with the file drawer explanation. Maybe we're only seeing a small subset of all the research that's been conducted. I know I have experiments that I've never published. They didn't go anywhere. Something was wrong. We didn't quite finish them. I'm sure many of you do too. So maybe the results that are missing have been file drawered. Those null effects have been hidden away. The third and most insidious option is that some of the data supporting null effects are published, but they're not published as null effects. They've been polished and formed into statistically significant findings. So they are null effects that are masquerading as statistically significant effects. Now, although that can happen through scientific misconduct or fraud, it can also happen in much more mundane and unintentional ways. As one example, let's say we have a researcher who forms a hypothesis, collects data, sits down to analyze it, and they run the analysis and find that their p-value just misses significance. Bummer. Okay, why might that be? Well, they look at the scatter plots to try to understand why the data turned out as they are, get a better sense of it, and they notice that there are some really extreme values in their data set. And they think those extreme values might be error, might be noise that are messing up the data. So they decide to exclude those extreme observations. This isn't deleting participants, it's getting rid of, like, let's say, reaction times that are way longer than average, which may indicate that the participant was checking their phone or something instead of, keeping their finger on the button waiting to respond. So we should get rid of them. Those participants don't belong in our data. And they get rid of those observations, excuse me. So they get rid of those observations and they find the p-value is a bit lower, a bit closer to that 0.05 threshold that will render statistical significance, but still not quite there. So, okay, the researcher thinks about it and they say, they remember that in addition to the main dependent variable of interest that they planned to analyze this data with, the data from that they're noisier than usual. There's more variability than what they'd expect. And they also happen to include another dependent variable that somebody else in the lab uses and wanted to see how it would compare to our main dependent variable. So the researcher thinks to themselves, Well, maybe we should create a composite of both of these variables. They're both supposed to be measuring the same thing. They're correlated with one another, and our usual measure is a bit noisier. So maybe making a composite measure would get rid of some of that error. So they do the analysis that way. The p-value is getting even closer to 0.05, but still not quite made it. But then they realize, oh, but a couple of the participants didn't complete that additional dependent variable. So we don't have full data from them. We just have the noisy original dependent variable. We exclude them too. And now, voila, we have a statistically significant finding. So this is a case study in p-hacking and running lots of analyses until reaching a desired outcome. So why do processes like this occur? Well, given pressure to publish and the structure of academia, all of the incentives in academia press toward finding statistically significant effects. And critically, it's also very important to note that all of these decisions that our researcher made are totally reasonable choices in some cases. There are lots of situations where it makes sense to exclude participants or to remove extreme observations or to use composite dependent variables. So none of these feel like you're doing anything wrong because these are all totally reasonable choices to make. So given that all of these things, that researchers may do all of these things for perfectly good reason, I think it's very easy for us to convince ourselves that the decisions we're making and the things we're testing out seem reasonable and make sense. But the point is that we are more likely to make those alternate decisions when the data don't fit our hypotheses than when they do. So as a counterexample, if the researcher ran their analysis and got statistically significant results, it seems far less likely that they would then still try composite dependent variables and look for things to exclude if those choices increased p-values, if that eliminated statistical significance. So we have a bunch of reasonable choices that we could make, but we make them primarily when we don't get what we expect, right? So if we have a bunch of choices, but we only selectively make them when the results are not statistically significant, then we have a clear method for increasing type 1 error rates, for increasing false positives. So in this example that I gave here of excluding observations, excluding participants, making composite dependent variables, this is just a really small subset of the choices that researchers get to make when they're conducting, when they're doing analyses and designing studies. So we refer to these choices as researcher degrees of freedom, and we all face a ton of them when we're working with our data. So in many disciplines, there is tremendous variability in the way that people make these choices. There are lots of cases where there is no gold standard, no one best way for making any of these. So as just one example, a lot of my work involves reaction times or response times, right? You give a participant a stimulus, they have to push a button as quickly as they can to respond to it in some way. And it is very common for researchers to exclude particular observations on reaction times. For instance, if I'm asking people to do a task where they say, is this a word or not? It's reasonable to have reaction times that are in the neighborhood of a few hundred milliseconds. People are typically relatively fast. And so if you have some response times that are like 8,000 milliseconds, that participant was clearly not doing the task appropriately on that trial, right? They were checking their phone, they were getting a drink of water, they were doing something else. And so we don't want to include those observations. So how do we decide what is too slow a reaction time? Well, we could opt to drop observations that are 2 standard deviations above each participant's mean reaction time. That's a thing a lot of people do. Maybe 2.5 standard deviations, maybe 3 standard deviations. Maybe instead of above each participant's mean, we should do the grand mean, or maybe some number of median absolute deviations above, or maybe anything over 2000 milliseconds, or maybe the slowest 2.5% of responses. All of those things that I just said, none of those are made up. Those are all choices that I've seen in published papers. And none of them is clearly right or wrong. The point is that there are just lots of choices that researchers are making. And it's clear that given enough choices, given sufficient researcher degrees of freedom, and given enough incentive to get statistically significant results, it's possible to make null effects look like significant effects. And I want to really emphasize here that I believe that many of the null effects masquerading as significant effects got into the literature without researchers consciously making a decision to p-hack or engage in other questionable research practices. I think it's very easy for these things to happen unintentionally and unconsciously. Okay, so where we are so far is that it's hard to publish null findings. And given that tenure and promotion and fame and fortune depend on publishing, we all are incentivized to get statistically significant findings. And researcher degrees of freedom provide the opportunity for researchers to influence whether their results are statistically significant. So where do we go from here? Many of the recent initiatives to improve psychological science and other disciplines have focused on the importance of transparency in the research process. People can't evaluate what you did if they don't know what you did. So this refers to transparency about what you did, both in data collection and in analysis, why you made the choices that you made, and when in the research process you made those choices. So one clear example of an increased push towards transparency is pre-registration, in which researchers specify in an uneditable timestamp document before they have collected their data, whether and how they will exclude participants or observations or use composite dependent variables and any number of a large number of choices. The document is then stored on the Open Science Framework or some other comparable platform. When the paper is eventually published, you include text pointing the readers to the pre-registration document so they can look back and confirm that you did exactly what you said you would ahead of time. So the benefits of pre-registration are that it limits the choices you can make after you've seen the data, and thereby limits p-hacking because you're specifying everything you plan to do ahead of time. Of course, sometimes things happen during data analysis that you didn't foresee, and it's fine to deviate from the pre-registered plan as long as you're transparent about it. So in my own research, I have inadvertently pre-registered that I was going to do something that turned out to just be a dumb choice. And so when I was analyzing the data, I didn't just do the dumb thing. I said, note, we had pre-registered that we were going to do this. Here's why we think it's a problem. So this is what we opted to do instead. So the idea is not that pre-registration limits what you can do, it just makes it clear what you plan to do ahead of time and what you decided to do afterwards. So the practice of pre-registration has just exploded in the last few years, and it's becoming increasingly common throughout the sciences. Another method for increasing transparency is what is referred to as the 21-word solution. So it states that researchers should be expected to affirm when publishing a paper that they have reported everything transparently. So they didn't just collect data till they got a significant p-value, they didn't kick out participants to get a significant result, etc. So this is text that researchers can put into their methods section to just affirm to affirm that they have determined sample size, data exclusions, and all of that. Now, although the 21-word solution does not prevent outright fraud, people can always lie, it means that researchers have to at least affirm how they got the results that they did. And it draws attention to the fact that not doing this can lead to problems. So proponents of the 21-word solution have made parallels with nutritional labels on food. Right? You have to tell people what's in their food. You should have to tell them what's in your paper and how you got to that point. One of the benefits of the 21-word solution is that it's free and easy to implement, and you don't have to have thought of it before you ran the study the way you do for pre-registration. Another solution to increase transparency is to change the method of scientific publishing. So rather than having data collection precede peer review, as it does in traditional publishing, in a new publishing format called registered reports, we make a detailed plan of exactly what we're going to do with an introduction and hypotheses and methods and an analysis plan, and submit that to the journal with no data. So before you have collected any data, you send the paper out for review. It then goes through detailed peer review, and eventually, if the reviewers and editors approve, the paper is accepted in principle, meaning that the journal agrees to publish the paper no matter what the results are. The idea is that if it is an interesting question to ask and the methods are sound, it is interesting no matter whether the results support the hypothesis or not. So in addition to the problems that are solved by pre-registering research, registered reports have the added benefit of avoiding publication bias. The study is accepted whether the results are statistically significant or not, thereby keeping non-significant results out of the file drawer and reducing pressure to massage those null effects into significant findings. There's a recent analysis. Registered reports have now been around for long enough that we can compare how registered reports, we can compare features of registered reports to traditionally published articles. And a recent analysis that looked at registered reports against traditionally published papers that were matched on a number of criteria showed that registered reports are much more likely to show results that do not support the hypotheses. So on the left is the 96% positivity rate of traditionally published papers that I referred to earlier. And on the right are registered reports, in which only 44% found support for their hypotheses. So here's what this means. If we remove statistical significance as a prerequisite for getting published, studies are much less likely to render statistically significant results. I'm sure you're all gasping. I wish I could hear it, but like that's a really big deal, right? The designs of registered reports are peer-reviewed prior to data collection, which means they are likely to be stronger than in traditional publishing. The sample sizes are typically larger because they're required to have a priori power analyses indicating they're sufficiently adequately powered. And the hypotheses and analyses are locked in ahead of time, meaning there can be no p-hacking. So what these results suggest is either a tremendous amount of publication bias at best, or p-hacking and other questionable research practices at worst. So as of this morning, when I checked, there are now 286 journals that currently accept registered reports, including those listed here and many others, and the number is consistently growing. So pre-registration and the 21-word solution and registered reports all contribute to greater transparency about how work was conducted and when in the process decisions were made. But it's important to remember that transparency does not necessarily mean good science. It does not guarantee quality. You can pre-register a badly designed study and no one may want to publish it. You can transparently report terrible analytical decisions. Just because it's transparent doesn't mean it's good. It can still be a terrible choice. But transparency is necessary for others to thoroughly evaluate the quality of the work. I sometimes see people using these kinds of open science practices like pre-registration or the 21-word solution and using those as kind of a heuristic for evaluating the quality of the science. And that's never what they were intended to be for. They were intended to increase the transparency, to enable us to evaluate the credibility, not to be a stand-in for credibility itself. But beyond these methods for increasing transparency, the last 5 years or so have also seen a huge number of other proposed solutions for dealing with the issues that led to the replication crisis. And I won't go into all of them here. I'm happy to talk about them in Q&A if people have questions. But the advances in the last 6 years, the new initiatives and programs and organizations dedicated to improving our discipline is really inspiring. I love doing science. I love being a scientist, and I'm committed to trying to do it in a way that is maximally robust and replicable and transparent. When I was asked to do this talk, I was also encouraged to present a more personal viewpoint about my own experiences and journeys as a scientist as well. So I started adopting open science practices in my lab at Carleton, the Perception Lab, several years ago. And as many labs do, our adoption was piecemeal and happened in steps. So we started off by sharing data and code and materials for newly published projects. And as part of that, we switched from using SPSS to using R for our statistical analyses to make our data cleaning and handling process more transparent. Because R is a scripting language, it means that each step in the data cleaning is documented. And so it's easier to go from raw data to completed analyses. We also started pre-registering our new projects as they were happening, and then posting preprints of our work in progress. So posting preprints means putting a PDF of your document on an online repository. We use SciArchive before it's published. So that means you can start getting feedback on it from other people earlier. It makes work accessible earlier, so it helps deal with the fact that sometimes the peer review process can take ages. And it also makes the work accessible to people who don't have journal subscriptions, which makes work be more equitably accessible. And then most recently, we've started publishing some of our work as registered reports. And again, if people have questions about what the process of doing a registered report relative to traditional publishing is like, I'd be happy to talk about that in Q&A also. So my experiences doing open science and teaching the undergraduates in my lab how to do open science have been very, very positive. I think they have increased, they have made my research more sound. They have made me more thoughtful as a scientist. And it has been really a joy to help teach students how to engage with these practices. In order to help others, give others resources to teach and practice these open science practices as well, I've written papers about the pedagogical benefits of doing open science with undergrads, and got funding to organize a workshop to help teach other faculty at small liberal arts colleges about how and why to incorporate open science in their teaching. If you want to incorporate open science in your teaching, you are welcome to draw from the whole online class that I teach about the path from replication crisis to credibility revolution. The link is in the corner. It includes lectures, activities, readings, and so forth. It's been really fun to engage with undergrads on these topics. And I find that training undergraduates in using open science practices and the benefits of using open science practices, I think really helps strengthen their training as scientists. So even if they don't go on to become speech perception researchers, I think armed with a really good sense of methodology and measurement is very useful to them to become informed consumers of science as well. All right, so I've been excited about open science for a while, but my involvement with open science and issues related to transparency and reliability got very personal a couple of years ago. So in 2018, I published a paper that I was incredibly excited about, along with a former undergraduate of mine, Violet Brown, who is now a WashU grad student in Kristen Van Engen's lab, and my wonderful postdoc mentor, Dennis Barber. So in that paper, we were looking at how visual information affects listening effort, which are the cognitive resources necessary to understand speech. And we presented participants with speech in masking noise that was sometimes accompanied by a visually presented circle that modulated with the amplitude of the target speech. It looked like this. So it's like a little visual cue saying, hey, speech is happening now. And thereby reducing temporal uncertainty, right? It's giving a visual clue about when listeners have to direct their attention. So relative to an audio-only condition, we showed that the modulating circle significantly and dramatically reduced listening effort as measured by faster reaction times on a secondary task. The effect was huge and dramatic. It was also very exciting because this has clear clinical and real world applications, right? We have a way of adding a simple signal generated in real time that makes listening to difficult speech feel easier. The paper whizzed through peer review. It was published in Psychonomic Bulletin and Review. I was delighted. This was also the first paper out of my lab that followed all of the open science practices I was endorsing. So it was pre-registered, it had open data and open code and materials. I planned follow-up studies, and I wrote and was awarded a National Institutes of Health grant to continue to fund the work. It was my first, big kid, now I'm a PI grant. Violet Brown replicated the study with older adults at WashU using the same program and stimuli and methods that we'd used at Carleton. So we were quite puzzled when we ran a follow-up study the following year to try to extend the effect, and found that under very similar conditions, the effect did not replicate. In fact, the effect was reversed. So the blinky dot was slowing people down. It appeared that seeing the blinky dot increased listening effort. So we tried to troubleshoot every possible reason that the results might have changed. We upgraded to a newer operating system, and we had different recordings of words, and they were at a different bit rate. Maybe that was it. We tried to come up with everything that was possibly different about the two versions of the study. We ran tons of pilot studies and spent agonizing lab meeting after agonizing lab meeting trying to pinpoint the problem. And finally, I found it in the program for the original experiment that presented the stimuli and captured participant responses. I had programmed in a mistake. I had inadvertently programmed a timing delay between when we started the reaction time clock and when the audiovisual stimuli, or sorry, when the audio only stimuli were presented. So to make this like a racing metaphor, I had basically pressed go on the stopwatch before the starting gun for the audio only condition, but not the audiovisual condition. So the audio only condition had artificially inflated reaction times. When you remove that error, the effect flips. The dot starts slowing people down again. So this tiny little programming error that I had made turned out to be entirely responsible for the results, completely explained the effect. The effect that we thought we had discovered that had cool clinical applications and all of that was just a programming bug. There was nothing there. So the central finding was a software glitch, and it was totally untrue. I had published a finding, published a paper that was just completely objectively wrong. I found the mistake when I was sitting in my house alone at my laptop. It was in the evening. I'd put my kids to bed, and I was just sitting there in the dark trying to figure out what was going on. And when I did, and the realization was like sinking in of what the mistake meant and what consequences that would have, I felt physically sick. I was shocked. I had published something that was totally wrong and had celebrated it and presented it at conferences and published it and gotten federal funding to keep studying it. And it was completely untrue. So I felt deeply embarrassed to have made a stupid mistake like that. Very disappointed. I loved this finding. So I was disappointed that it was junk. I felt guilty for wasting other people's time reviewing it and publishing it and polluting the literature. And I felt super worried that admitting this mistake and retracting the paper would jeopardize my job and my grant funding and my professional reputation. I know what retractions can do to people's careers, although retractions can happen for lots of reasons, including this, like honest mistakes. The majority happen because of scientific misconduct or fraud. So even though it would be the right thing to do to reveal the error, I was terrified to do so, especially because I had my grant for less than a month. It was brand new, and I was currently under review for tenure. Like my committee was literally meeting the following week. So to be completely honest, I thought about not telling anybody. I thought about just trying to conceal the mistake. And I thought maybe I'd get away with it and no one would ever know the truth and I wouldn't have to share this embarrassment and risk my career. I also thought that maybe I would have to tell people, but maybe I could tell them just like in 6 months after I have tenure, after I have published something on the grant, that is related, that makes it clear I can do some research. So it would have been easier to not say anything or to at least delay saying something. And all of the incentives were pushing against transparency here. So here I am, alone in the dark, crying my face off, and the only one who knows, right? Nobody else knows, and with everything to lose. As fate would have it, just a few weeks before I discovered the error, I had given an interview about my work in open science for the magazine of the American Psychological Association. And the article had ended with this quote of mine. As scientists, we should not be in the business of hiding when we're wrong. We should be looking for ways to be less wrong, but if we are wrong, it should be out there so other people can find it. That is what makes science self-correcting. It's a good quote, right? It turns out that is very easy to say when you don't think you've made any mistakes, but when you have, it's a really hard thing to actually grapple with. So, okay, so I'm sitting in my living room making my choice, and I had my words, we should not be in the business of hiding our mistakes, echoing in my ears. So as you can tell, obviously, I made the transparent choice and decided not to hide this. I lay in bed awake all night, just feeling miserable. And then I got up and I had the worst day of my professional career. I spent all day emailing and calling to share the story of how I had screwed up. And the list was devastating. I had to call my co-authors. I had to write to the journal editor to initiate the retraction. I had to contact the National Institute of Health program officer. tell my sweet research students who look up to me and respected me and hope they still would. And given that I was under review for tenure, I had to write to my department chair and the dean of the college to explain. I remember saying to my husband that morning before I left for work, I said, I don't know if this will end my career, but it's in that ballpark. So what I was struck by that day, in addition to how much it sucked, was that everyone that I talked to, my colleagues and my dean and my co-authors and the editor of the journal were kind and supportive. The editor said, bummer that these things happen. Thanks for letting us know. We'll figure it out. My dean said, I'm impressed with your integrity. And then of course also, and we'll make a note in your file. Okay, but ultimately, the journal opted not to retract the paper, but they instead published a revised version of it with the results updated to reflect the true and opposite results. I got tenure. The NIH didn't revoke the grant. There was enough other stuff in the grant that was still relevant and interesting questions to be asked that I had proposed that I still have it and can pivot and kind of explore other things that are related. So everything worked out far, far better than I feared that it might have. But I realized that in that moment where I'd found the error, sitting alone in my chair, in my dark living room, deciding whether or not to make the right transparent decision, I didn't know how things were going to turn out, in part because I had never heard of a comparable situation. I had heard of people finding mistakes early in the research process and having to rerun experiments. I had heard of people who had problems in their research exposed by others, but I had never heard of anyone who found an error in their own published paper that invalidated the results and voluntarily shared it. So I had no idea what was going to happen to me. And that's one of the things that made it really hard and scary to bring this mistake to light. And I realized that moment, alone in the dark, deciding between personal advancement or security and scientific integrity is a moment that many other scientists must have had, and many other scientists in the future are going to have. So even though things worked out well for me, it would have been possible to not share the embarrassing story of my error to a wide audience, I decided that I should share what had happened with others so that when in the future someone else finds their own mistake, they have a model and they have some reassurance of what might happen. So I decided to write an essay and share publicly and describe this whole experience. And I hoped that being transparent and sharing more publicly the result that disclosing a mistake didn't sink me would inspire others to do the same when they had the opportunity. So when someone else is sitting in their dark living room making their choice, they are less terrified by the possible unknowns. I also realized that even though I found this error at a precarious point in my career, pre-tenure, freshly grant funded, there are far more precarious situations, right? It would have been harder if this were my first paper ever, if I was a grad student on the job market, if I was from a historically excluded group, so I already faced challenges being taken seriously as a scientist, if I were term or adjunct faculty, any number of things. So this is truly a situation where people who are the most established would be the least negatively affected. So I wrote this essay and I shared it nervously on Twitter. And I hoped that it would get some traction because I wanted it to reach my intended reader, who is a scientist who someday finds a mistake in their own work and has to decide what to do about it. And the response that it received online was incredibly heartening. I wanted to share this story so that people could see that admitting a mistake doesn't have to end your career. It's an added benefit that now people could see the outpouring of support for transparency. So today, over 50,000 people have read the essay, and more than 500,000 have read the story on Twitter. And as ambitious as I am about my own scientific work, I think it's safe to say that the original listening effort paper would never have had the same impact. I've heard from many researchers who've said that they're making the essay required reading for all incoming students, and others including it in their courses. Since I've posted the essay, I've been contacted by 6 other researchers who have found mistakes in their work and are trying to figure out how to deal with them. So I have like literally listened to people cry on the phone and reassured them that they're doing the right thing and this doesn't undermine their value as a scientist. Making mistakes is part of being human, and normalizing that as scientists is necessary to making our discipline more transparent and more robust. The essay recently was awarded a commendation from the Society for the Improvement of Psychological Science for helping to promote transparency and openness. And as a result, I was also able to share the story and contribute to a recent piece in Perspectives on Psychological Science about correcting errors in our own published work. So this paper just came out, and it was really an honor to be involved with it. It was heartening to see many other researchers, including at least a few WashU alums and former faculty, be willing to admit that they had doubts about one of their own previous findings, either as a result of making an error or conducting a statistical analysis they later learned was inappropriate, or even through p-hacking. So my hope is that being willing to admit when we are wrong will also help to foster a more positive culture around self-correcting. So it seems that in response to the question I posed earlier, what leads to false positives in the literature, in addition to questionable research practices, another way false positives get into the literature is through error, just by people messing up. Mistakes that lead to null effects may be lucky enough to get file drawered, but mistakes that are statistically significant may get published. So another step toward trying to reduce false positives in the literature is to try to minimize the mistakes that we make. Jeff Rauter and colleagues have a terrific paper in AMPS called Minimizing Mistakes in Psychological Science, in which they distinguish between issues like pre-registration and structural changes from mistakes. Rauter calls these mistakes bonehead moves, which is really a pleasure to see in print, like using the wrong data set, transcribing errors, saving over data files. And I'm sure that all of you who do research have seen mistakes happen in your research or in your labs. And they can lead to minor annoyances like wasting time or having to redo an analysis or run additional participants, or they can have much more negative consequences like having to retract a paper. And there's been a lot written about best practices for things like data management and independent checking of code and these other methods of preventing errors. But it is still incredibly common for papers to be published without using those best practices. So my guess is that most of us have been authors on papers in which only one person wrote the analysis code and no one else checked it, or where only one person programmed the stimulus presentation software and no one else checked it, or where only one person checked the stimuli to make sure they were properly labeled, or checked the numbers in the manuscript against the output from the statistical software. And any place where only one person is checking anything is a very weak link in the research process. Because making mistakes is just something that happens to human beings. And simply trying to be careful is not enough to ensure that mistakes don't happen. Despite our best efforts, anyone can make mistakes. So how can we move toward avoiding these kinds of bonehead moves? Rauter and colleagues argue that the first step is conceptualizing of mistakes as shortcomings of systems, not shortcomings of individuals. One of the people who reached out to me about finding an error in their work was a postdoc who ran their analyses using what they thought was the appropriate covariate, but turned out to be the participant ID number instead because of ambiguity in variable names. And the postdoc felt terrible for having made the mistake, but I pointed out that if the lab had a system that ensured that every analysis is checked by someone other than the person who wrote it, that error would have been caught. I think it's totally unreasonable to expect that all of us and all of our students can avoid making mistakes. But what we can do is set up systems to reduce those mistakes, to try to catch them before they surface. So the best step toward reducing errors in our labs is ensuring that we're setting up systems that make it less likely that we make mistakes and more likely that we catch the ones that we do make. So I've been thinking for a long time that I wanted to come up with some kind of set of resources to help other researchers identify systems to make fewer mistakes. And so in order to try and facilitate this mistake prevention for busy lab groups who may not have time or inclination to read all of the papers on best practices in data management, I've begun putting together a project called airtight, exercises for lab groups to prevent research mistakes. It identifies a number of places in the research process where errors can occur and highlights lots of mistakes that other people have made. One of the recurring themes when people talk about mistakes in research is, it just never occurred to me that XYZ could go wrong. So my hope is that by offering up examples of ways that things have gone awry for others, that this will be helpful in kind of stoking people's creativity about where things can go wrong for them. It then lays out some suggestions for how to avoid errors and how to catch them. So it emphasizes in particular standardization of any steps that can be affected by human error and detailed record keeping and transparency. And the initiative is designed to be an exercise in self-reflection for labs and help them identify ways that things can go wrong. It is not a set of one-size-fits-all guidelines, as the approach that labs take will vary depending on the kind of research they do and their tools and so forth. So as just one example, here's a subset of error type, including some of the possible errors during the data collection phase. So let's say that someone is programming a new study and changes the settings of the eye tracker that's used, that's currently being used for another study. So after that point, data collected on that computer isn't usable. So a prevention solution would be to implement rules about programming or working on computers that are currently in active data collection mode. Another would be setting clear rules about what can and can't be changed on computers that are involved in running. Some labs can't separate computers that are currently being used for data collection and those that are work computers. So a step that doesn't require that and doesn't prevent the error, but does prevent the impact of the error, would be to keep detailed records about which participants were run and on which computer and by which research assistant. So if you later find the error, you can identify which data you have to throw out and which you can keep. So in this set of exercises, I'm sharing a number of mistakes that I've read about or heard about or made myself, and some suggestions for how they could have been avoided. And the exercises are really intended to encourage researchers to read through them and then outline their own research pipeline and identify points of weakness and discuss how they might implement systems to avoid errors there. If you would like to explore this for yourself, the first draft of the project is available now in the Open Science Framework. You are the first people I have talked about this project with publicly. It is still very much in the early stages, but I thought this would be a nice opportunity for me to present it to a friendly crowd. And if some of you are interested in trying it out in your labs, I would love input and feedback from you. I'm going to be doing some of the exercises in it with the CCSN students on Wednesday, and then I'll update the materials based on input from them and other people I've reached out to in the community. And so if any of you elect to use these resources, I'd be very happy to hear from you about how it went. And if any of you have ever made mistakes, I'd be interested to hear about them so I can incorporate them as well. So finding a major mistake in research was really hard for me, and it has been really hard for the 6 people who have contacted me since. And I'm sure for many others who haven't contacted me or decided to make a different decision. But my hope is that by encouraging others to come up with ways of avoiding mistakes, we can work toward strengthening the literature and avoiding the heartache associated with making mistakes in science. I think this is a really exciting time to be a scientist. I am inspired by the changes that I've seen in the field, and it's heartening to find ways that we can all improve the work we do to help science become more truly self-correcting. If you are interested, these slides are publicly available on the Open Science Framework at the link on the screen. Thank you very much for your attention, and I'm eager to hear your questions. Thank you.
Thank you so much, Julia. I hope it became clear to those of you on this call that, there's a unique story that Julia had to share, and she shared it in this call. It was what prompted us to invite her to deliver this content, not only the pedagogical material on Open Science Framework, but a very unique experience with it personally. In my knowledge base, I don't know anyone else who's had quite this kind of an experience. So right before we transition to the Q&A session, I want to invite all of you that this is the idea behind the workshops that we're doing for CCSN, to provide a behind the curtain account or accounts of science in practice, how methodology has been thought through carefully to affect neuroscience research. And if you are aware of other anecdotes or experiences that you think should be shared more widely with your classmates, your colleagues, the CCSN community generally, please let Shelley or me know. We're planning out the future workshops now, and we think that this is the kind of content that would be most beneficial to students.